MIRI is one of the 4 instruments on board the James Webb Space Telescope. It's the one instrument on board the telescope that will be observing at mid-infrared wavelengths. The other instruments focus on the near-infrared part of the spectrum.
NIRSpec, NIRCam and the FGS, they work at wavelengths from about 1 to 4 or 5 microns. Now MIRI is unique on the James Webb because it operates at even longer wavelengths than that. So we start at 5 microns and we keep going out to 25, 30 microns.
MIRI is actually quite a complex instrument. It has several different observing modes on board in the instrument. So we have a camera that just takes images in lots of different filters across the mid-infrared wavelength range. We also have spectroscopic modes, so we have low-resolution spectroscopy, and we also have a medium-resolution integral field spectrograph.
When you look inside our own galaxy, you can see dusty regions, and there's things going on inside those clouds, inside the dust, that you can't see because dust is essentially opaque. If you move out to longer wavelengths, out into the infrared, the opacity, the amount of light that is absorbed by that dust drops, and so we can see not just the surface, but into the heart of dusty region. So that means we can see to the center of our own galaxy more easily. We can see inside dusty regions where stars are being formed and see them, see what's really going on when a star is formed in space.
We're really going to be able to address a huge range of science questions. MIRI is going to be able to probe even further back into the history of the universe. It's going to be able to really study the atmospheres of planets around other stars and really be able to kind of search for the signatures of molecules in those atmospheres. Those are just a few of the highest kind of profile science goals that we hope to achieve with MIRI.
Amateur scientists discover galactic bubbles. Presented by Science at NASA. Our galaxy gets its name from a luminous band stretching across the sky on warm summer nights. Innumerable stars in spiral arms blend together to form a milky river of light that literally cuts the heavens in two. Ancient Greeks called it the Milky Circle, or in classical Latin, Via Lactea, the Milky Way. Modern skywatchers might have found a better name, though. Dom Perignon. A team of more than 35,000 amateur scientists have been looking through images taken by NASA's Spitzer Space Telescope, and they have discovered more than 5,000 bubbles in the disk of our galaxy. The Milky Way's disk is like champagne with bubbles all over the place, says Eli Bressert, an astrophysics doctoral student at the European Southern Observatory. Bressert is a professional astronomer who has been analyzing data from the Milky Way project, which harnesses the power of citizen scientists to explore space. Computers can find these kinds of structures, but none can yet match the power of the human eye, notes Robert Simpson of Oxford University, principal investigator of the Milky Way project. Humans are particularly good at noticing the wispy arcs, partially broken rings, and circles within circles of overlapping bubbles in the crowded galaxy. The Milky Way project taps into the wisdom of crowds by requiring that at least 5 people flag a potential bubble before adding it to the catalog. We have plans to try and use data from the Milky Way project to help train computers to perform this task better, adds Simpson. Interstellar bubbles are a sign of star formation. Fast-moving winds from young, hot stars blow bubbles into the surrounding gas and dust from which they are formed. Because stars are born in groups, the bubbles tend to crowd together, overlapping in ways that can trick computers. People, on the other hand, are finding more bubbles than researchers thought possible. These findings make us suspect that the Milky Way is a much more active star-forming galaxy than previously thought, says Bressert. Spitzer is an infrared telescope that can see long distances through the dusty plane of the Milky Way. Infrared vision is key to the bubble hunt. Star-forming regions are deeply embedded within dust in the galaxy, explains Simpson. Ordinary visible light has trouble penetrating these areas. You need infrared or radio wavelengths to detect them. Bubbles are so numerous, researchers suspect they must play an important role in the evolution of the galaxy. For instance, rapidly expanding bubbles can run into interstellar clouds of gas, triggering bursts of star formations as the clouds collapse. New stars, in turn, blow more bubbles. It's a cyclical process that could keep the Milky Way fizzing like a gas of the bubbly. Curiously, the center of the Milky Way seems to be fizzing less than it should. The number of bubbles counted by volunteers drops off around the galactic center. We would expect star formation to be peaking in the galactic center because that's where most of the dense gas is, says Bressert. This project is bringing us lots of questions. Anyone who would like to help find the answers can join the Milky Way Project at milkywayproject.org. For more news of galactic importance, please visit science.nasa.gov.